It works. Alright, that's enough of that. Let's get into the design by taking a look at my first attempt to reach 200 darts per second. I laid out the concept behind this design and the issues it had in my last video, so I'd recommend you check that out before this one. To sum it up, it had two major issues: lack of motor torque and the drum disengaging from the roller. A lot of you had some great ideas on how to fix those issues, with a ton of you suggesting adding a flywheel, which is an excellent idea. Gold stars for all of you. However, the little roller responsible for moving the drum down was by far the weakest link. It did not take much force at all for the drum to disengage and cause the darts to jam. Adding a flywheel won't fix that, but I'll keep that idea in the back of my head though. I got some other comments suggesting different thread shapes, different ways to move the drum down, and ways to reduce friction. A couple of you even suggested lubricating the darts?
What is that?
Vaseline,
Why?
to make it go faster?
Ew.
Yeah, I agree. Anyway, I do appreciate all the comments and the input, so keep that coming. Now let me show you what I have planned for version 2. Let's start with the original design, hide all the stuff, and get rid of this ill-fitting stepper motor. The next thing to go is the problematic roller and central shaft. I'm going to use two motors this time, one connected to these drive shafts and another connected to the central lead screw. A nut on the dart drum will connect the two motors together. This main motor will spin the drum, and the second motor will spin the lead screw to pull the drum down, fully replacing the plastic roller. I made a scale model to test the concept. The dart drum moves freely along two drive shafts and spins with the main motor. The second motor only spins the lead screw. To accelerate the drum, both motors spin up in sync, and once up to speed, the lead screw motor changes directions to pull the dart drum down. This scale drum has a pitch of 2.5 millimeters, which means for every full rotation, the drum should move down 2.5 millimeters. Since the lead screw has a much smaller pitch of 0.7 millimeters, it has to quickly spin in the opposite direction for the drum to move down 2.5 millimeters per rotation. To be more precise, if the drum is spinning at 120 RPM, the screw will need to spin at 300 RPM in the opposite direction. For the full-scale design, I thought I could use these lead screws with a 2mm pitch commonly used on 3D printers. To fire 50 darts per second, the drum needs to spin at 190 RPM. To move the drum 0.6 inches down per rotation, a 2mm screw would need to spin at 1300 RPM. As the drum approaches 760 RPM to reach 200 darts per second, the screw will need to spin at an insane 5200 RPM. That was way too fast, so I hopped on good old McMaster-Carr to find a lead screw with a pitch much closer to the dart drum. I managed to find a screw with a 1/2 inch pitch for a surprisingly cheap $14. With that pitch, the motor's speed at 200 darts per second goes down to a much more manageable 180 RPM. With the drum threading hopefully solved, I still needed some strong motors that could be precisely controlled. The ODrive S1 controllers paired with these big motors should be the perfect solution. Big thanks to ODrive for providing these for the project. With all the components picked out, I finished designing everything and got started with the build. Before I spent the time to make the rest of the components, I wanted to get the program as solid as I could in case I needed to change the design. Let's take a look at the components I'm using for now. I'm using two of these large ODrive motors, each driven by an ODrive S1. The drives are powered by an adjustable 0 to 48 volt power supply currently set to 24 volts. On top of the power supply is a voltage converter that supplies 5 volts for the Teensy 4.1 that controls both motors. This other breadboard is the user interface. It's got a 2-axis joystick, a simple OLED display, and 4 buttons connected to this I2C I/O expander. I wrote a simple program to control the motors with the joystick, and after a bit of messing around, I noticed that the drum motor was shaking the frame a bit. I loosened the drum motor and saw how much wobble there was from the drive shafts. A simple adjustment of this piece fixed that right up. Mostly. I wrote another program to test the drum motion at higher speeds. The next step was to make the motion a bit more automated, but first I had to define a few things about the drum's motion. The drum's position will be defined by its distance from the drum motor Z and its angle of rotation, theta. Right here, Z is 0 and goes down to negative 5.8 inches. Theta will be 0 right here and increment counterclockwise. I removed the mini drum and replaced it with this thing with a magnet in it. I also added a magnet sensor here. Next, I wrote a homing sequence to define the Z and theta values. The drum gets pushed until it hits the end of travel and rotates the drum motor, marking the Z position 0. The drum is then pushed into the other end to measure the travel distance. Finally, the drum moves to the magnet sensor and rotates until the sensor is tripped, marking the rotation 0. I then wrote a program to simulate the drum motion. The drum moves to the left, both motors spin up to 120 RPM, and once the drum's angle is 0, the screw motor starts spinning at 30 RPM in the opposite direction until the drum reaches the end. To test the motion accuracy, I cut this piece of cardboard for the magnet to weave through. The spacing matches the pitch of the dart drum, and the notches are about 1/16 of an inch wider than the magnet. I spun it up to 180 RPM and it wove through the cardboard just fine. When I doubled the speed, yeah, that didn't work. It hit the cardboard because I'm assuming the lead screw motor accelerates instantly. In real time it does look instant, but this slow motion footage shows that it's not. Conveniently, you can set how quickly these motors accelerate. Currently, they are set to accelerate at a rate of 100 revolutions per second squared, which means it will go from 0 to 100 revolutions per second in 1 second. In this slower test, the motor changed speed in 38 milliseconds. In the faster test, it took 75, and at the target speed of 760 RPM, it will take 157 milliseconds. During this acceleration, the drum moves a currently unknown distance before it locks in, so to speak, and starts moving down properly. This red spiral here represents the path of the dart drum once it's locked in and moving down, and this hole represents the barrel. Quicker acceleration will start the path earlier and slower acceleration will start it later, misaligning the path from the barrel. To compensate for this, the release angle of the drum can be adjusted until the path lines up with the barrel. To calculate the release angle, I need to figure out how far the drum moves as the motor is accelerating. I did a little bit of calculus and came up with these equations. All I need to do is plug in the drum speed and the acceleration value of the lead screw motor, and it will pump out how far the drum will move during acceleration. At 180 RPM, the drum will only move 0.035 inches, and as the speed approaches 760, the distance jumps all the way up to 0.6 inches. Going back to the two tests earlier, the faster test moved an extra 0.1 inches further, which explains why it hit the cardboard. Before I use this to adjust the release angle, I'm going to use it to stop the drum a set distance from the end. When the drum gets close to the end, the lead screw motor is told to accelerate to the speed of the drum to stop its motion. Currently, there is no compensation for the drum movement as the lead screw speeds up. In each of these tests, the drum should have stopped 1.5 inches from the end. With different acceleration rates, the actual distance varied quite a bit. I ran the same tests, but this time told the drum to stop 0.5 inch from the end plus the calculated acceleration distance. This time the end gap was much more consistent. I'm not sure why each overshot the goal, but at least it overshot consistently. With that out of the way, I started working on calculating the release angle. I did some geometry and eventually landed on these extra equations. I implemented them and it still hit the cardboard. I triple checked my math and didn't find anything wrong with it, so I decided to measure the motor's acceleration and see if the problem was there. It took 115 milliseconds to accelerate and 86 milliseconds to decelerate when each should have taken 60. Seems like that could explain things. Alright, let's take a quick break and talk about the two types of control loops, open and closed. In open loop systems, the controller tells the motor to move and just kinda hopes it does correctly. A good example would be most 3D printers. Each stepper motor is told to move precise amounts, causing the extruder to print whatever shape you want. This system works great until something keeps the motors from moving. Without feedback from the motors, the controller has no way of knowing if a motor stopped and continues to print as if nothing happened. Closed loop systems add a feedback sensor to close the loop. This way, any disturbances can be detected and corrected. A good example would be these ODrive controllers. The ODrive reads the requested speed value from the microcontroller and tells the motor to move that speed. If an outside disturbance causes the motor to slow down, the controller can detect that and increase the motor current to speed it back up. To adjust how aggressively the ODrive reacts to disturbances, you can adjust a parameter called velocity gain. Raising this number will make the ODrive react more quickly, so that's what I'm going to adjust to fix this slow acceleration. I plotted the expected acceleration and then started measuring the actual acceleration starting at the default velocity gain. I raised it until the total acceleration time got much closer to the calculated 50 milliseconds. While the total acceleration time got closer, the velocity curves never really matched this calculated one. There's about a 10 millisecond delay before the motor actually starts moving, and when it does, it's not necessarily a straight line. This is an issue because this little equation assumes a perfectly linear acceleration that doesn't start 10 milliseconds after I tell it to. It might be possible to compensate for the delay in slightly curved acceleration, but I wasn't sure if it would be worth the effort. Instead, I decided to focus on doing closed loop control. Even though the two ODrives use closed loop control, the system as a whole is open loop. The microcontroller tells each motor to move a certain speed, but does not check if they are moving that speed. If one of these motors were to slow down for any reason, the path of the drum will be thrown off and never corrected, just like the layer shift on the 3D printer. At first I tried to simply tie the speed of the lead screw to the measured speed of the drum motor, but that didn't work. There's about a 100 millisecond delay between the motors that caused the drum to drift a bit as it accelerates. I'm not sure why that was the case, but I'm sure I was doing something wrong. After some more thinking, I decided it would be better to calculate the path of the drum and use the lead screw to do course corrections. Essentially, I'll calculate the expected z-value of the drum based on its current angle. If its actual z-value doesn't match the calculated value, I'll use the screw motor to push or pull the drum into position. My first stab at it looked promising, but it quickly got worse with speed. I plotted my calculated path for the slow speed and compared it to the path for the faster one. Besides the starting acceleration, these should match exactly. For whatever reason, I had the hardest time figuring this out. After many hours, rewritten math equations, and contemplating all the choices that led me here, I finally figured it out. Mostly. At slower speeds, the calculated path had brief jumps that caused massive overcorrection. At higher speeds, those jumps went away. I need to get rid of those jumps, but after all those hours of trying to figure it out, my brain was absolutely fried. I decided it was good enough for now and moved on with the rest of the project. Wait a second, what is this? That's right, it's the sponsor of today's video, PCBWay. PCBWay is a manufacturing company based in China that provides many services great for projects, including CNC machining, 3D printing, sheet metal fabrication, injection molding, and of course, PCB manufacturing and assembly. For this project, I ordered a couple of circuit boards and a thumbstick printed on an SLS 3D printer. The ordering process for both of these was very quick and simple. Basically just check a few boxes, drag and drop the build files, and submit the order. If you need parts for your project, head on over to PCBWay, link in the description. Thanks again to PCBWay for sponsoring this video. Alright, back to the build. Okay, you get it. I did some soldering and now the build is done. Let's take a look at some of the new parts. I replaced the base breadboard with a custom circuit board and also the interface breadboard with another custom circuit board. The interface got a larger display and smaller joystick. I needed a way to launch the darts out, so I stole the motors and electronics from this Nerf turret. I've got a couple videos on this build, so check those out if you're curious. I put the motors next to the barrel, and on the other side, the speed controllers, power distribution board, and signal isolation circuit. The main power supply is still set to 24 volts, but these speed controllers can only handle 16.8. High current voltage converters aren't exactly cheap, so I chose to use a battery instead. It's stored in the base with its own power switch and voltmeter. Since I had to start the design from scratch, I took the opportunity to fix a lot of flaws that the version 1 design had. Getting rid of the roller meant getting rid of the roller groove, which let me decrease the drum's pitch. That, combined with an extended dart channel, increased the dart capacity from less than 50 darts to around 80. I also swapped this 1/8 inch acrylic for 1/4 inch ABS, increased the fastener size from 2.5mm to 4, and used threaded brass inserts instead of threaded plastic. The dart shell also got a nice upgrade. The old one mounted to a crappy 3D printed shaft collar that wobbled quite a bit. The new shell mounts directly to the drum motor and spins much better. The old 3mm shafts were prone to twisting, so I replaced them with 6mm ones spaced further apart. The old roller assembly was also pretty flimsy, so I made it much more stout. The cut-up tape measure used to lead the darts out on V1 was hot glued to the inside of the barrel, which made replacing it inconvenient. I replaced it with a piece of printer filament and attached it to a servo. It's now easier to replace and can get out of the way during the homing sequence. When I powered everything up for some testing, the display didn't look right, and when I moved the motors, they just kept going. I decided to measure the I2C signal and noticed how smooth the signal was. These edges should be more square. It also doesn't help that I routed the wires way too close to the motor wires. Instead of routing the wires somewhere else, I bought this I2C signal booster from Adafruit. With it hooked up, the signal got much cleaner and the screen stopped having issues. With that out of the way, I worked on fixing those jumps in my calculations. These jumps were always the same amount, the exact pitch of the dart drum. To fix this, I added this little if statement. Basically, if the actual and calculated z-values of the drum differ by about the pitch of the drum, I just subtract the pitch of the drum. It's not the most elegant solution, but it works well enough for me. With the program finally working, I was ready for my first dart tests. I started off small at 30 darts per second and worked my way up from there.
What was that?
That was the stupid programmer's fault.
Didn't you program it?
Evidently, the motor didn't have enough torque, so I bumped the power supply up to 42 volts, which is close to the limit of this voltage converter. I also found this sneaky little checkbox that limits the motor torque to 20%. I unchecked that, rebooted the motor controllers, and did another round of tests, this time starting at 95 darts per second. The last dart ended up getting jammed in the drum and destroyed the lead out. Good thing it's easy to replace. I upped the speed again and the last dart got stuck even worse. The gap for the dart lead out is very wide, so it doesn't take much force to push these foam darts into it. I 3D printed these little pieces to make the gap more narrow, and I tried to push a dart through it. Not even close. There's a large gap for the plastic lead out to pass through. It works pretty well. I also noticed that the drum wasn't quite lined up with the barrel, so I adjusted its position. For this third round, I wanted to be a bit more scientific with my testing. I loaded exactly 30 darts in the drum and measured the speed and current of each of the motors. Oh nice, new record. I wasn't sure what happened there, so I looked at the slow motion and saw that the darts pushed up against the drum shell and broke through the gap in the plastic. Some tape should fix that. As soon as darts start pushing out, the motor speed dips and the electrical current rises sharply. This brief spike of energy is the perfect application for a flywheel. A flywheel is a heavy disc that is spun up as a way to store energy. The heavier the disc, the more energy it can store. I replaced this 1/4 pound piece of plastic with a 2.5 pound steel disc, so it should help quite a bit. I'll use the initial acceleration of the drum to store up energy in the flywheel, which will then be used to help push darts out. With the flywheel installed, it was time for another round of tests.
Holy crap.
The flywheel without a doubt increased performance, both by increasing darts per second and decreasing the peak motor current. One interesting thing to point out is the fact that the flywheel didn't really start helping until it got faster than 500 RPM. This can be explained by looking at the formula for flywheel energy. As the speed goes up linearly, the energy goes up exponentially. Before I tried to go faster, I decided it was time to hook up the drone motors. The speed of these motors is controlled by a common PWM signal, which stands for pulse width modulation. It consists of 1 to 2 millisecond pulses that are repeated every 20 milliseconds, which is a 50 Hz signal. Varying the width of these pulses will vary the speed of the motors. These motors and controllers can produce large voltage spikes that can make their way back to sensitive electronics, such as this microcontroller. To protect it, I have this circuit that isolates the speed controllers. This isolation is achieved by using a chip called an optocoupler. The input signal powers an LED which shines light onto a light-sensitive transistor. An inverted version of the input signal is then produced on the output side of the chip. Since this inverted signal no longer has 1 to 2 millisecond pulses, it can't be used to control the motors. I need to invert the input signal so the output has the proper pulse width. On the project I stole these motors from, I was using a microcontroller that ran MicroPython. Inverting the signal is very easy, so I figured it would be just as easy with Arduino. Apparently the only way to produce a custom 50Hz PWM signal is by modifying the existing servo library. I opened it up and had no idea what I was looking at. Like, what does this even mean? I gave up trying to modify the code after a couple of hours and got this inverter chip instead. I'll input the PWM signal into the chip where it'll be inverted and sent to the isolator, which will then invert it again for the speed controllers. It's kind of messy, but at least it works. With that done, I moved on to the 5th round of tests. I added 50 darts to the drum this time and started at 160 darts per second. I upped the darts to 70 and went even faster. Well, that's not good. I didn't exactly know why it jammed, so I emptied the drum and did a dry fire test. For the first couple of rotations, the dart channel wasn't lined up with the barrel. It was able to correct itself halfway through, but that obviously wasn't good enough. I slowed the drum down a bit and checked the alignment. That looks better. I then loaded in 50 darts and went for it. Oh dang, that looked fast. Let's count the darts. And there it is, 200 darts per second. With this thing finally working, it's time to do some real-world testing.
That was good though. I think that's usable. That was fired fast. Yeah.
If you're wondering, yes, I did completely miss both of them, and no, I do not want to talk about it. Anyway, if you enjoyed this video, give it a like and subscribe to the channel. If you really enjoyed this video, consider joining my Patreon where I post exclusive project updates. Link in the description. Anyway, what should I do next? Should I go for 300 darts per second? Should I put this thing on a turret? Something else? I don't know. Anyway, see you in the next one. Peace out.